Okay, ladies and gentlemen, let's take a look at functions as a series. Now, the whole point of us going through the arithmetic geometric series is because those functions can act as a series of polynomials. So let's start here. If I say a sub n equals a sub 1 times r to the n minus 1, that is the formula for finding any term in a geometric series. Now, remember, a geometric series could be any function of some initial value, say 4 people, for population of 4. And we have some sort of rate, and we're going to double. So that's going to be a rate of 2 raised to the n minus 1. And now I can find, after 3 cycles, I would plug in 3 to this, and that would give me the number after 3 cycles of an initial value of 4 doubling every time. So that's an example of a geometric series. Okay, now we know that a geometric series could also be written as a list and a sum of terms. So we say, well, if you have this mean the first generation, that means second generation, that means third generation, on and on and on. So we just find each of the individual terms. But if I put them in a summation, I'm going to find the first term, then the second term, then the third term, then the fourth term, then the fifth term, all the way over and over and over. In fact, if I were to set this equal to infinity up here, I could find the sum of all of the various terms going all the way from 0 to infinity. And it's 0 because 1 minus 1 is 0. Now, so the first term in a geometric series is a sub 1 r to the 0. The second one's a sub 1 r to the first. Third one's a sub 1 r to the second, on and on and on and on. However, why write the a sub 1 over and over and over again? Why don't I just take the a sub 1 and put it out front? That leaves me r to the 0, r to the 1, r to the 2, r to the 3, etc., 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 on and on and on. For not shocking reasons, this is called a power series. The reason it's called a power series is because it's a series of variables raised to a power. Now, in this case, it's the constant radius r. Now, we know that this series will converge, meaning it will have some sort of approximate value that is finite as long as the ratio is absolute value is less than 1. So as long as it has some sort of fractional ratio, it will converge. Now, if it's double in this case, it's going to diverge, so the sum is going to be absolutely infinite regardless of what you do. But if the absolute value of r is less than 1, it will converge. So in this case, then the series converges if the absolute value of r is less than 1. If that happens, we can simplify this summation to simply be the sum is equal to a sub 1 over 1 minus r. That's our shortcut. Because as this goes up, if this is fractional, a fraction raised to infinitely higher powers is going to get closer and closer and closer to 0. So the shortcut is this. So if we set a sub 1 just equal to 1 rather than 4, let's say we have a starting population of simply 1 and make it easy. And we replace r in this series with x. Now I have x to the 0, x to the first, x to the second, x to the third. And shockingly enough, that's a power series. Now, that means we could also go from right here and replace this r with x and this a sub 1 with 1, allowing me to have this as my series as long as it goes to infinity. If that's the case, then I can also replace a sub 1 and r here and make 1 over x, and now it becomes a function of x. So 1 over 1 minus x is a function of x. The whole point is if I have some real graph, if I have some real graph that I'm attempting to estimate, I could use a straight line as an estimate, but that would be a poor estimate. That would be if I only use the first of the sum. If I use the first 2 terms of the sum, it becomes a straight line. Well, that's a better estimate than a horizontal line, but not awesome. I could go the first 3 terms and say my estimate is x sub 0 plus x sub 1 plus x squared. And now that becomes a better estimate because I get the curvature, but it's going crazy over here. If I go with the third term, now it goes to x cubed. Well, the thing is, the farther I go, the better an estimate of the actual graph the polynomial becomes. So this idea of polynomial estimation using a power series is all related back to how good an estimate do you want. How far do you have to go to get a quality estimate of some graph you don't know? That's the basis of what we're going to be doing. So we'll pick it up in the next video.